We're going to work on collecting like terms, and we're going to actually try to put together the algebra of collecting like terms, so that's the actual numbers we look at, along with these concrete materials, which are called algebra tiles. Okay. This is a question directly out of your homework. It is definitely a more difficult question. There are many terms involved. 2, 3, 4, 5, 6, 7, 8. We have 8 terms. So we've got to get through a couple definitions first. First of all, the number in front of any variable is called the coefficient. Okay. So when we are collecting like terms, we're focused on the coefficients. Okay. When we have a letter, symbol, anything representing an unknown number, that's called a variable. Okay. Now, we have what looks like many different coefficients attached to quite a few different variables. To collect like terms, we have to make sure our variables have the same exponents or powers to them. Okay? So what we're going to go through is I'm going to highlight things that would be like terms. First of all, I need to find another number in this that has an x to the power of 2. Do you guys see any of them? Right.
The last one.
The last one. What does that say?
2x squared.
Okay, good. Now, is it just 2? Yeah, so we're going to take the actual operation in front of it. These two here are considered like terms. Their variables have the same exponent. And that's what's important. We don't need to look at the coefficients. The coefficients is telling us how many of them there are. Okay. The next one, we have our coefficient. Again, not the most important part. But we have 2 variables attached to it. So in this case, I need to find another term that has the exact same 2 variables attached to it. Does anyone else see another term like that? Logan. 5xy. Positive 5xy and negative 3xy will be considered like terms. Now, you may be confused. This looks like a subtraction sign, so saying minus, minus, plus, plus. But when we're collecting like terms, as long as we keep the operation in front, we can move things all around. So I'm going to collect the last set of like terms here for us. We actually have nothing else that has a y squared to it. This is the only one. And let's use orange. This is the only value that has y to the power of 1. But we do have 2 numbers that have no variables attached to them. Does anyone know what those are called? For us, they're called the constants. T-S. Okay. So these are our constant terms. And constant terms can be added and subtracted together without any difficulty. Okay? So essentially, they're considered like terms in themselves. So our constants here can be put together. So we've highlighted everything that can be collected and put together as a like term. All right, so we have our like terms. Now, we do have algebra tiles here, and it is going to take a bit to represent each of these. So, this 2x squared, the idea of this 2x squared here, is that we're taking this tile here, x squared, and we have 2 of them. Okay? So, in other words, to represent that, I would take 2 of these bricks, and we have 2 x squareds here. In our next example, we have 3 xy's. Okay? And in other words, that's the combination of an x and a y. So this is only one set of that. I actually need 3 of them. So we're going to copy and paste. Oh, is it negative? Excellent. You're 100% right. It is negative. So both of these values we've used are positive. So these are not the values we're going to be looking for. Thank you for pointing that out. We need actually a negative. Yeah, I guess that idea will work for now. Okay. So we have a pair of them. Nice and easy. That's the good thing about computers. Okay. So we have 3 sets of the negative 3xy's in this case. Okay. Our constant term is negative 6 here. So we take our negative 1, and we're just going to duplicate it 6 times. And the reason we're doing this is because we're going to be using these to cancel out other values. Okay, how many do I have? 6? Beautiful. 4y squared. In other words, that's our y squared. And we're just going to duplicate this tile 4 times. our 7 is positive, so I'm going to take the positive values of my 7. And the reason we're taking these different values is because we're going to be using them to eliminate other numbers as we go through. For instance, as I'm pulling these down, a negative 1 and a positive 1 will cancel each other out. Okay? So this negative 1 and this positive 1 would cancel each other out. So we're eventually going to combine them to get rid of them to see what we're left with in terms of constants. Here we're left with our positive xy, and I should have just took what I had before. Here's our x and our y. And in fact, we need 5 of them, so I'm going to probably need a little more room, just because it's getting a bit crowded here. So let's paste a whole bunch of them. 2, 3, 4, 5. There we go. So we have 5 sets of them. Remember, these are sets of. There are actually 10 tiles altogether, but each of these tiles is representing an x and a y together. So we need 5 sets of the x and the y together, just like we needed 3 sets of the negative x and negative y. We have negative 3y, which means we're taking our negative y tile and taking 3 of them to represent it. There's a whole bunch of tiles. That's why this is a tough question to work with that way. And finally, we have negative x squared, which means we're taking 2 of the negative x squared tiles. So, algebraically and with these concrete materials, we're going to start canceling values out. Okay, so I want you to think of this idea. Wrong button. A positive x squared and a negative x squared will do what to each other? They'll cancel each other out, okay? So I essentially cancel them out, so I'm going to continue to bring these together. Do I have any other positive or negative x squareds? No. So they've canceled each other out, and that algebraically makes sense to us. What is positive 2 and negative 2 together? 0. So essentially we have, and I can write it this way, 0x squared. Now, do I need to include this term? What is 0 times any number? 0. So it essentially cancels itself out. So our pairing that we highlight in yellow is gone. Okay? We're then going to take our negative xy's and our positive xy's. And these are going to cancel each other out also. Okay. So we'll take each grouping. There's one grouping, 2 groupings, that's right, 3 groupings. I apologize, it takes me a bit of time. Okay, so I've eliminated all of our negative ones, so what am I left with? Positive 2xy, which again algebraically makes sense. Let's look at our values. What is negative 3 plus positive 5? It's 2. So we have 2xy to start the next line. Okay, so that's what we're left with. We'll do the same thing, and I'll do it actually very quickly with our constant terms. I have 6 negative ones and 7 positive ones. What are we going to be left with? We're going to be left with 1. These 6, along with, can I control? Yes. These 6 will all delete each other. They'll cancel each other out, and we're left with nothing. So we have one constant term, which is positive 1. Okay? How about our y squareds? Do we have any negatives to cancel them out? No. So we're still left with these. Oops, sorry, I didn't mean to do that. We still have our 4 y squareds. And how many negative y values do we still have? 3. So we write these values in. And just as you noticed from before, there were no like terms to eliminate these, so they stayed as the exact same values. So we had positive 4y squared minus 3y. This is technically your answer. Now, a lot of times they want you to write it in a very specific order, and the order they usually want you to write a polynomial in is the order with the variable that has the highest degree. So normally we would start this with positive 4y squared. Then, if our variables are the same, anything that's combined would be the next term, so our positive 2xy. Then our negative 3y plus 1. And if you want to see where those all came from, okay, this was our positive 4y. This was our positive 2xy. This was our negative 3y. And finally, our last term, which is positive 1. So your answer was 4y squared plus 2xy minus 3y plus 1. Okay. Now, we don't always have to use algebra tiles to solve this, but we didn't.